Okay, let's go ahead and get started here. I want to welcome you tonight. My name's Tim Swindle. I'm the director of the Lunar and Planetary Lab here. And this is the third of our lectures in our fall lecture series. And it's, we've had good crowds, good lectures. I gave the last one, so I know it was good. So I don't have a lot of things to announce coming up in the future, but one I want to mention is that on Wednesday, December the 4th, we are going to have a free exhibition of artwork based on planetary science, a combination of pieces of art, original art based on planetary science, and pieces of images from planetary sciences that really qualify as art. We've got over 100 pieces of artwork that are going to be here, so that should be fun. For the spring, we do not have a lecture series, but Stewart Observatory will still have their Monday lecture series. And the College of Science lecture series this spring, running through February, is, do you remember what the topic is this time? Don't remember. But those are the ones in Centennial Hall that are always quite good and worth checking. Yeah, they're finishing the off-campus series on happiness, yeah. So we can't be happy in February. But anyway, and just some other things to note. You've probably seen some of the countdown clocks out in the atrium here that we have for the countdowns to various missions. There's one launching to Mars in something like a week. You can find out the exact days, hours, and minutes out there. And in about 2 weeks, we will turn on another countdown clock, the countdown to the OSIRIS-REx asteroid sample return mission that is being managed out of LPL. Will hit 999 days, and so that's where the countdown clock starts. We'll have a new one starting in December. So this evening's lecture is going to be about how the Antarctic is helping Arizona keep its cool, and the rest of the world as well, and the Southern Ocean, which used to be called, I don't know, people never knew what to call it until it officially became the Southern Ocean a couple of decades ago, something like that. The water around Antarctica. And our speaker this evening is Joellen Russel. She got her bachelor's at Harvard, her PhD at Scripps, and then came to Arizona from Princeton, where she was working. She described herself as an Earth systems modeler. Did I get that right?
That's right.
Which means a little bit of ocean geochemistry, a little bit of climate modeling, a little bit of, this is interesting stuff. And she is an associate professor of geosciences and planetary sciences, and we are delighted to have Joellen Russel this evening.
Thanks, Tim. Tim was on the search committee that brought me here, and so I've always wanted to return the favor by really paying off on the investment, So one more down payment. Here we go. But I want to talk to you today about the Southern Ocean. I'm very glad to be included in this sort of planetary scale science, because wait till you see. This is really cool. So I want to just acknowledge my collaborators at NOAA's. This is the National Oceanic and Atmospheric Administration's Geophysical Fluid Dynamics Laboratory. These are some of the best climate modelers in the world, and they collaborate. I collaborate with them on their fantastic Earth system models. Tom Delworth, John Dunn, Steve Griffiths, Bob Hallberg, Ron Stauffer, and Mike Winton. And I just got back from my sabbatical at Princeton, and where these guys are, and I have to make sure I put in a plug for them. So what I want to talk to you today is about the Southern Ocean and what it's doing for our global climate, and particularly for places like Arizona, where it's arid and where it's warming. And that's a lot of the planet, actually. So what you're looking at here is actually the sea surface height differential in the Southern Ocean. And what is represented by this big drop-off here is what they call the Antarctic Circumpolar Current. It is the world's largest current by a long shot. It is 172 million cubic meters of water per second. All the rivers in the world are 1 million cubic meters of water per second. All of them. This is 172. The next largest current in the world is the Gulf Stream off the east coast of the US, and it only carries 40 million cubic meters of water a second. This is by far the big daddy in climate. This is it. For ocean stirring, this is the one. And the reason it's so important is it's not just a surface current like most other currents in the world. This current in particular is so strong, it actually scours the bottom of the ocean. you'll actually find basalt right under the main axis of the current, and particularly where it's concentrated through a fracture zone or fault, what you'll find is big drifts at the end of the fault or the fracture zone, because in fact it has scoured the bottom and dumped the sediment out on the other side. So it's basically just mowing along the bottom in this massive top to bottom current. And this has huge implications for what happens when we would like to store, say, a bunch of heat in our deep ocean, which is really almost 0 degrees of Celsius. It's basically very near freezing. And this would be a great way to sort of store a bunch of heat, fractionally warming the deep ocean, but keeping us relatively cool. And that's actually what's happening. So let's look. It's complicated down there, and it's complicated because we have these massive westerly winds. We have westerlies in the northern hemisphere and in the southern hemisphere, but the southern hemisphere, because we have so little friction, i.e. no great big speed bumps like the Rocky Mountains or the Himalayas, so we have no speed bumps in the southern hemisphere the same way. We have the Andes, but they only poke down into the westerlies of the Southern Ocean just a little bit. So essentially, those westerlies are 30% higher than they are, stronger than they are in the northern hemisphere. And what it does is it drives this massive current all the way from top to bottom. And of course, there's no blocking it, right? The ocean is open all the way around. So the winds crank around and the water cranks around in this big, huge blender that really is represented all these different processes. So what happens is the winds blow along, they push water away from Antarctica all the way around, always pushing water away from Antarctica. What that does is you can't have a hole in the ocean, right? Can't have a hole, so it fills in, but it fills in from below. And unlike everywhere else in the world ocean, where the deepest upwelling you might get is 200 meters in the tropics on the equator where we have easterlies, in fact, the deepest upwelling in the world occurs here, and you wouldn't believe me if I told you, so I'm going to actually have to show you. But the water upwells from somewhere between 2 kilometers and 3 kilometers deep. I'm not kidding. It comes up 20 to 30 football fields. From that depth, it comes all the way to the surface. And let me show you what it looks like. So essentially, because we have this unbounded current, meaning there's no blocking it, it doesn't have run into land anywhere, it basically goes round and round, and it has all this upwelling. Notice where the green is here. We have all this water coming up to the surface, up here, up from every basin. Essentially, the whole deep ocean is ventilated, basically gets more gases and exchanges mass with the atmosphere in the Southern Ocean. This is it. The deep ocean connects to the atmosphere through the Southern Ocean, almost exclusively. Okay? So this is really important for our total planetary, balance of carbon and heat, because of course the ocean is very cold, especially the deep ocean. So what we're looking at is all that water that's ventilated, again I'm going to use this word, basically Antarctic Intermediate water, where you see this AAIW. Basically what you're looking at is all of the ocean's, what we call the warm layer that sits right on the top, the thermocline, all that warm water that sits on the top. We have a little bit of push of colder water just underneath it, which is full of nutrients and fertilizers, etc. And everywhere it's green. And the reason we've colored it green is because it underlies that surface water and produces a lot of the nutrients that are necessary for global production in the ocean. Absolutely essential for global productivity, because this is where all that lovely cold, rich water comes from. It came from the deep and was pushed out underneath these warm waters globally. Notice that the influence of the North Atlantic is much, much smaller. You don't actually see the North Atlantic ventilating, except here's our Labrador seawater, here's our Mediterranean water. Kind of different, huh? So when you're looking at it in a slice, like through a layer cake, here's the Southern Ocean down here, this is the Antarctic, this is the North Atlantic. We're cutting through the Atlantic here, and we're looking at salinity. What you notice is here's North Atlantic deep water, here's this high salinity water, and up, 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 it comes to the surface. And this is you just looking at a salinity distribution with your naked eye. There it is. Comes down, and there's the tongue just kind of sticking right up to the surface. So I'm actually showing you, this is that water upwelling from very, very, very deep around the Southern Ocean. So this is fantastic. And you would think that this would be taught in every class and that everybody would know about this in terms of earth science and climate science, that this is so important. But in fact, we had some modest measurements of the Southern Ocean, but because those winds, remember the 30% higher, and it's so far away and it's so rough, I've spent almost near a year of my life down there in the Southern Ocean on ships of different sizes and varieties. And all I can tell you is the ocean is trying to kill us. I'm not kidding. Oh, gives me black sweats just to think about it, because you're in these waves that you think could not possibly be any bigger. I keep asking my friends when they go down, because I never took any video. I have a few horrible snapshots, out the deck window, out the bridge window, but you can't see anything. You can't see anything because when it's that rough, it's black. First, you get a little spray on the deck window, which is, a story above the deck, right? It's up, the bridge window is. So there you are, little spray on the window. Ooh, it's getting a little choppy. And then it starts to turn blue, and you're like, starting to get a little rough out here. Woo! Pretty soon the water's dark blue, and you're like, I'm still working, it's fine. I'm not going to worry my mother yet. And then you come up, chug, 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 this 300-foot ship, and you start to slide down the wave on the other side, and it's like you go 0G, all of a sudden weightless, whoosh, and you can feel it coming down, and then all of a sudden, dig into the next wave, and it just drops on you like a mountain of water, like so much water that it's black on the bridge. You can't see the sun anymore. It's very scary. But these waves can be up to 100 feet high. I personally have seen them be 60 feet high. And really, when it was even rougher, I couldn't tell because I didn't want to look anymore. You just felt like at any moment, you would just be crushed like a beer can. Like you go down under the wave and it just would never come back up. But in fact, you can work down there. But ever since then, I've basically been working on other ways to work on the Southern Ocean than from inside a ship. So first I'm going to tell you about climate models, and then I'm going to tell you about satellites, and then I'm going to tell you about autonomous floats that don't involve my going to sea anymore. I laugh, but it's really true. I'm dedicated to not having to do that anymore. So what is the role of the Southern Ocean in the global climate system? It accounts for up to half of the annual oceanic uptake of anthropogenic, i.e. human-made carbon dioxide from the atmosphere. Half. This is an agreed-on number. This is not a squiffy number. There's 7 different data sets that says it's half. Vertical exchange in the Southern Ocean is responsible for supplying nutrients that fertilize 3/4 of the biological production in the global ocean. 3/4 from the Southern Ocean. It may account for up to 70% plus or minus 30%. That is not a misnomer. That is the best number we have of the excess heat that is transferred from the atmosphere into the ocean each year. And the Southern Ocean winds and buoyancy fluxes are the principal source of energy for driving the large-scale deep meridional overturning circulation throughout the entire ocean, i.e. stirring and mixing the whole ocean. Southern Ocean is the big daddy in climate. It really is. After clouds, the next thing we need to know is how much heat and carbon are going in around Antarctica. That's it. So why are we worried? Because of this curve, which is actually carved on the wall of the National Academy of Science. I got to see it. It was really cool. I used to sit, he died a few years ago, Dave Keeling, but I was lucky enough to be at Scripps when he was still there, and of course would park myself at his lunch bench. At lunch, they had these picnic benches out by the beach, and he would sit and have his lunch, and I just spied him and was like, ha. Being the enterprising young graduate student, I quick bought my lunch and brought it down. It was great. He even had dinner with my parents up in Montana. It was unbelievable. Very nice man. So the trajectory of global fossil fuel emissions, we're basically on our upward and upper end of the emissions trajectories that we could be on. Although in recent years, we've actually seen a decreasing total emissions from the U.S. as we've moved slightly from coal to natural gas and had kind of a mini depression. So the CO2 emissions, if you just looked at growth rate, it was about 1% a year in the 90s. It was about 3% a year average in the 2000s. But of course, we've had a couple of rebound years that were closer to 6%. At that rate, you're basically doubling CO2 in 40 years, which is just an outrageous. I mean, we were thinking 100, right? Meaning most of our scenarios that we look at are roughly doubling in 100 years, not doubling in 40, which would be where we would be if we were on this sort of trajectory. So just as a, sort of heads up, this is what's coming. So there's a net imbalance in the top of the atmosphere, and we know this from the Earth's radiation budget experiment, ERBE. He's fabulous. Come on, we've got this great satellite that looks out and looks in and basically says, this is what's coming in and this is what's going out. And hey, there's a growing imbalance. Where is that heat going? Well, we've actually done, Kevin Trenberth and others have done fantastic reconstructions of where all that heat is going, looking at all the data that you can assimilate. And what you get are these lovely climate change indicators from the observations. So this is land surface air temperature from 4 data sets. You can see the recent growth. Sea surface temperature from 5 data sets. 2 data sets for marine air temperature. Sea level data sets, 6 of them. And here are 5 data sets on summer Arctic sea ice extent. And essentially, we're really looking at overlapping answers. There's very little real uncertainty between these. So where is all the heat going? And everybody is always surprised, I think, when I tell them that, in fact, what we're looking at in the atmosphere is a teeny-weeny residual. It's just a little tiny difference between what's really going into the ocean and what's going back out to space. There's those 2 parts, and then there's the atmospheric heating. So essentially, there's 2% going into the atmosphere, 2.1 in the continents, about 1% into glaciers and ice caps, 0.8 into the Arctic sea ice melt, 0.2 into the Greenland ice sheet, and 0.2 from the Antarctic ice sheet. And you could look at this in other ways. This is from the new IPCC 2013 report. What you're really looking at is down here in purple, which you bet most of you can barely see. This is the atmospheric global. This is the energy going into the atmosphere. It's that tiny purple band. The brown is the land, the white is the ice, the dark blue is the deep ocean, and the light blue is the upper ocean. That's a lot of heat, and it's mostly going into the ocean. And over time, more and more is going into the ocean. So, this is relative to 1971, okay, within the distinct components of Earth's climate system relative to 1971. So when we look at this, and we actually get, here is the total net energy change, including melting of Arctic sea ice, Greenland, Antarctic, and glaciers. And here's the net radiation. And here we've actually got this missing energy. Everybody heard about this plateau in atmospheric heating. So we've been looking for this missing energy, right? Because it's not warming the atmosphere the way we quite expected. It's still warming, but it's not warming as quickly as we thought. So the net radiation as measured by satellites must be balanced by increased heat content on Earth. Well, on land, we're doing a pretty good job of measuring it. We are. In atmosphere, we're doing a great job of measuring it. But there is one spot we're not doing a really terrific job of measuring. This ocean heat content change is really only the top 700 meters. It's only the top 700 meters of the ocean, which go to 4 to 5 kilometers down. This is only actually a small fraction. What are they missing? They're missing the deep ocean. Okay, so where in the deep ocean? This is at 3,000 meters, and we've peeled the Earth like an orange here. That's why the funny projection. But what you're really looking at is, notice the bright red. And if, I don't know, you probably don't remember the number that was on that net radiation imbalance plot was we were missing 0.9 watts per meter squared. I just want to point out that here's this little number down here, which is the total in red. It's 0.9 watts per meter squared. And just by the way, those were totally independently calculated. They really were. This paper came out 2 years before the other one. So this is an estimate. But it's an estimate based on deep ocean surveys where people went to sea like I did and made lots and lots and lots of casts of a CTD, a conductivity, temperature, and density measuring device that basically that brings up bottles of water and makes measurements as it goes down and comes back up. So the Southern Ocean, here's the ocean warming globally in the brown, and this is the warming rate in degrees C per decade, and this is also out of the IPCC report. And what you're looking at here is the Southern Ocean in purple. It's warming from top to bottom. Now there's big uncertainties in this because it is so unbelievably hard to make measurements down there. But what's interesting about this is that it's measuring at about the same rate, roughly, from top to bottom, which should be basically impossible, right? It should warm a lot more at the surface and very little at depth, but instead it's mixing all the way to the bottom. And that is really exciting. One other thing I might mention is with this mixing, so we're actually mixing in a lot of the man-made carbon dioxide too. About half of the total anthropogenic uptake is happening in the Southern Ocean where we've got all this mixing. And it's being distributed with great depths because of that deep mixing. So the problem we have is that there are all these processes that have to be captured in a model in order to actually add up all these numbers and make them all balance, et cetera. It's quite difficult. And we have all these challenges as well. We have all the different aspects of vertical exchange, buoyancy fluxes, but also things like acidification. Meaning we know that as you add CO2 to ocean water, you basically are forming carbonic acid, which acidifies the ocean slightly. And over time and over massive amounts of CO2 input, we're basically changing the pH of the ocean. It's becoming more acidic. And what that does is makes it much, much more difficult for our calcifying organisms like coral reefs or pteropods or coccoliths, which are the phytoplankton, the grass of the ocean. They struggle because their shells are thinning. Okay, so carbon uptake is kind of interesting because there is a lot of carbon in the ocean relative to the atmosphere. So as we increase atmospheric CO2, over time, before we hit a threshold roughly somewhere between 1925 and 1950, the Southern Ocean would have been outgassing because you're bringing all this water from deep, and that water, when exposed to the atmosphere, had excess carbon. Basically, all the dead bodies of all the plants and all the animals that had died and rained down into the deep ocean, right? And then been, by bacteria, turned back into their component parts. All of that material would have been degassed back to the ocean as CO2. Except that the overburden in the atmosphere of CO2 has been increasing. And we've hit that threshold, blown right through it. So at this point, the Southern Ocean is ingassing more and more every year as we increase the CO2 in the atmosphere, which is pretty amazing. And what it's doing, and this is a projection, this is the potential this is the surface water aragonite saturation state in 1994, and this is what we project it will be in 2100. You'll notice that the rest of the global ocean isn't doing great, but it's not doing terrible. The one place where you'd expect it to do terribly is in the Southern Ocean. And the reason is that deep water with all that very acidic, very old water that's had 1,000 years to accumulate old organic material and be remineralized by bacteria. So we're worried about this. Well, so how much water is coming up? Should be easy to measure, right? It's only horrible waves, bad winds, very remote, on tiny ships in a huge area with different fluxes and great big storms, and it's changing at the same time, and it's incredibly expensive, maybe $40,000 to $80,000 a day to take a ship down there. Oh, by the way, they hate it when you go below 50 degrees south. They make you take on extra insurance because of all the icebergs in the water and the remoteness and the fact they can't get to you, and the only person who could ever rescue you that far would be like the Navy, and what if they don't have anybody in the area? It's really bad. So the models actually, so the data has a problem because we don't have enough of it, and the models have a problem because one, we don't have enough of it, and two, we're not sure if our equations are exactly tuned right for this ocean, which is pretty unexpected. So here is where that outcrop, remember when we had those water coming up to the surface and exchanging along these mixing surfaces, these density surfaces. So we see this big warming, and it's getting deeper and deeper into the ocean. But the problem is that we're not actually knowing how much we're changing the actual mixing in the Southern Ocean. So even if we were looking at how much is warming, is the warming also changing? That was, sorry about this, technical difficulties. We were just getting to the good part. Did I find it? Oh, there we are. Great. So, what we're worried about is, so we're warming all of this, and we're dependent on the ocean taking up all this heat, and we've got this fantastic mechanism for getting it down deep. But what happens if you warm a lot of water and you load it on top of this wonderful mixing mechanism? What happens? What if it quits? What if it slows down? That would be, if it slowed down even a little, that would be, let me show you what it would be. It's not good. So trends in the westerlies. Let's just start with the atmosphere. What happens if the westerlies change speed? Or, because of course they're driving this big current, right? So what happens if they change speed or if they move? And okay, the punchline is they did. They've already changed speed and they've already moved. So we have an experiment to do here. So basically, we have these westerlies in the southern hemisphere, westerlies in the northern hemisphere, and basically they're a function of how hot it gets in the troposphere, the lower atmosphere, at the equator, you know, rising atmosphere, nice and warm, and then our very cold poles, right? So the gradient between our cold poles and our warm atmosphere helps determine how big those westerlies are. So you'd expect that as the tropics warm, if the poles warmed faster, you'd have slower winds, right? If you had flatter gradient, you'd have slower winds. If you have a sharper gradient, say you warm the tropics but you don't warm the poles, you'd expect faster winds, right? Sort of straightforward. But the problem is up until about 7 years ago, we believed that, of course, the gradient would weaken because we'd warm the poles first and then the tropics would warm a little more slowly. So basically over time we go like this, right? And that would basically mean that we didn't actually, we'd have weaker winds which might stir less vigorously. In fact, the exact opposite happened. The troposphere warmed, and it turns out that because of changes in the polar vortex in both the northern and southern hemispheres, but particularly the southern hemisphere, we ended up with colder wintertime poles. At the same time, we ended up with very warm tropics, right? We're warming in the tropics. So, in fact, they cranked up, not down. And this is new. This is, you know, in the last 5 to 7 years, basically, where we thought what would happen is as we went into, say, the last glacial, where it was much cooler in the tropics, well, cooler in the tropics, but much cooler at the poles where we had the big ice sheets, that in fact, the whole troposphere kind of collapsed a little bit and our winds would weaken. And we think that's actually what happened. And then in the modern, as we're warming our tropics, that we'd tilt out toward the pole, but ever so gently. But it turns out we did two things. We had CO2 to warm our tropics, and then we had ozone to help cool the poles. And this is a problem. So this is what your westerlies look like if you just slice through the planet in the atmosphere. You basically got our southern hemisphere westerlies and our northern hemisphere westerlies, and you can see that the southern hemisphere is stronger. Up here is our boundary between the lower atmosphere where we have all our weather, the troposphere, and the stratosphere. And basically this is what you might call the jet stream, right, on either side. And the surface winds are basically just the lower expression of those aloft jets, right? And the aloft jets are basically a function of the gradient here and the gradient here. You'll see what I mean in a second. So what's happened over the last 30 to 40 years is basically a poleward shift of the winds. They basically tilted out and cranked up. So what you're looking at here is an intensification of the winds towards Antarctica and a weakening further out. Same thing in the northern hemisphere, but it's a little more asymmetric, again, because of those speed bumps I talked about, the Rockies and the Himalayas. It's not quite as symmetric and pretty. So this is what happens when you put it into one of those lovely climate models. You basically project that, in fact, as we get greater and greater CO2 in the future, this is a lower kind of business as usual. This is where we control emissions pretty well, and this is where we burn it all. You expect to see a poleward shift in the westerlies, and that's actually what we project and what we've seen just over the last 30 to 40 years. When you tilt those westerlies out, what you'd expect to see is that the wet areas get wetter and the dry areas get drier. And the reason is we sit in these dry zones, right? The westerlies only dip to us a few times every winter, maybe 3 to 5 storms these years. In a good year, we might get 7 or 8 storms, maybe. We can imagine that there was a year when that happened. It's been a while, hasn't it? Well, it turns out that it's less and less likely that those westerlies will reach us because they've been moving poleward. And as they move poleward due to global warming, we're basically getting drier and drier. But it also means that more and more wind energy is basically concentrating right over the Southern Ocean. Because while it's bad for us in the Northern Hemisphere, it's fantastic if you're mixing in the Southern Ocean. You've actually intensified it down here. So we're projected to get drier, and the Southern Ocean is projected to get wetter. And this is true across models. So if you attribute, actually figure out who's responsible here, you can see we tried each, this is not me, this is Arblaster and Meal, fantastic paper, where they basically ran the model with just volcanic forcing, just solar, just greenhouse gases, just sulfate, just ozone, and then lumped them all together. And basically this is the signal we'd expect to see, which we'd like to see, which we've seen so far. And this is what you get from just ozone forcing, changing the ozone concentration at the poles. That ozone hole that everybody thinks is recovered, but which isn't, yes, that's what this is. So here's the history of chlorofluorocarbons, or freons, the way we used to call them when it was just DuPont, right? Is essentially, yeah, good old-fashioned better living through chemistry, except for this one little glitch. And this little glitch is pretty serious, actually, because we all know about, we worry about UV, right? Because if we have less ozone, then we have more UV getting through, and we basically end up with skin cancer. Well, the problem is that, in fact, what happens is when it blocks, when it catches a photon, an ozone molecule catches a photon, it breaks apart in an exothermic reaction, one that gives off heat. So when it catches a photon up in the stratosphere, it keeps the stratosphere relatively warm because it gives off heat. No ozone, no warming, and more skin cancer for us at the surface, all right? So these are all linked. So what happened is basically everywhere in the world over the last few decades, since we've ripped open the ozone hole, the stratosphere, the upper atmosphere, is cooling. So if this were a solar problem, global warming, right, you'd expect the stratosphere, the troposphere, and everything in between to warm, right? All together now, more sun energy, more warming. What we actually see is warming down near the surface, and up in the stratosphere, it's cooling because, of course, we have, because it's a totally man-made fingerprint here. This has nothing to do with the sun. This has to do with us. So this is what we see from radio sun data, and it's everywhere. So anybody with a water balloon that would like to compare their profile over Tucson to way back when, you would see this cooling in the stratosphere and this warming in the troposphere. It's pretty amazing. And the ozone hole, of course, and this is just through 2011. I meant to update the slide and haven't. But basically, we're looking at the extent, the size of the ozone hole here, and the lowness of the ozone within the ozone hole, the minimum ozone. And it's a big ozone hole. So here's just the 2006 data, just so you can see what it looks like. And it's right over Antarctica. Here we go. And whoomph! Look at that. Isn't that beautiful? I mean, well, it's very ugly if you think about things, but amazing. Just amazing. Look at how coherent it is, too. It takes so long for it to break down and rip apart. It really is amazing. All right. So we can do simulations of this, and this is actually in a model. This is no longer in the atmosphere. This is a model. And what you're watching is, here's time down here with this little red bar. You're going down, 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 as we're opening up the ozone hole. Wait, here it's coming. And there's a little red, a little more. And we're dropping like a rock down here. Now it's permanent. Every spring. And we could run this out and it gets more intense. But basically what I also wanted to show is here's 2030. It's projected to recover, but slowly, very slowly. And in fact, out to the end of this simulation, 2100, in this model, it doesn't recover at all. It recovers a little, but not very much. So if your next question was, well, when the ozone hole recovers, and it's going to recover soon, of course those winds are going to collapse back to where they were. No, it's not going to work like that, unfortunately. And here, by the way, is the Arctic. This is not the Antarctic anymore. This is the Arctic ozone hole in 2011. This is the one over the northern hemisphere. I just find that fascinating. It's not normal at all. So what happens is, here's ozone depleting substances and their impact on climate. And this is what we would expect as it recovers, right? We're getting a peak roughly now, and sometime soon, with a little variability, it'll start to recover. And if you looked at the greenhouse gases, actually, the problem is that as this is starting to recover, what's happening? We are ramping up the impact on the winds by the warming. So as the cooling stops having such a big impact, the warming is taking over for it. So forcing with ozone depleting substances and forcing with just the greenhouse gases. And this is basically just looking at what the mean position of your westerlies. So climate models. We are using climate models to look at these things in the future. It's the only crystal ball we have is math. Lots and lots of very good, very sound, very well-tested math. And it's basically computer code that solves differential equations of air motion, ocean motion, thermodynamics to obtain time and space dependent values. And it's amazing. This is not actually exactly the same math we use for weather prediction, although we're starting to converge here. But it's, we are basically use a whole world, and we've had to do it at pretty low resolution up till a few years ago because it's so computer intensive. So we started in the 70s with just CO2 and an atmosphere with rain, no clouds, just some rain. And the 80s, we ended up with land surface, some ice, and some clouds. The next assessment, we ended up with a swamp ocean, which eventually became a real ocean, which actually then we added aerosols and a carbon cycle. And in this latest simulations done in support of the Intergovernmental Panel on Climate Change's new report, we have a full carbon cycle. We have phytoplankton. We have krill that eat the phytoplankton. We actually have biogeochemical cycles, deposition of carbonate on the bottom of the ocean. You know, we have the full enchilada, the full carbon cycle in the biogeochemistry. We're even including nitrate, like fertilizers, et cetera, and how they are cycled through the Earth systems as well. So we're actually getting to this, where we've added chemistry, et cetera. So this is, and stratospheric and ozone chemistry as well, because it turns out to be absolutely essential to getting those westerlies right. It's complicated. It's over 2 million lines of code. We run one of the versions of this model here at the University of Arizona's data center. But we're including all these processes too. Solar radiation, land surface processes like vegetation, reflectivity, topography, land use, all kinds of different kinds of clouds, sea ice, you name it, it's in there. Kitchen sink at this point. The one thing we're still working on, and by the way, this is a simulation. This is not data. This is just the ocean temperature you're looking at from a simulation from one of the models that actually we've now surpassed. This is one of our better efforts last year. And you're just looking at the Agulhas rings coming off of the tip of South Africa here. You can see here's the Cape. Remember, there's one side where you get very warm water and one side that's still cold. We actually get right down to that tip. And we're not prescribing this, right? What we put in was topography, greenhouse gases, and sun. And the rest is solving itself. And we keep track of every atom of carbon, right? All the energy, all of it, every watt. And all the water, every molecule in the model. You're looking at tropical instability waves here. You're looking at the loop current in the Gulf of Mexico and around the tip of Florida. The models have come a long, long way from things we used to use in the 80s. So here's our Gulf Stream heading out into the North Atlantic. It breaks off right where it should, off the Georgia's bank there, off the tip at the Georgia border. It's pretty awesome. So this is just a simulation, but we've gotten a lot better at it. So we're sitting at about this resolution. We're now down to about the 10-kilometer resolution. We were working at the 1 by 1 degree, which is roughly 110-kilometer resolution. And we'd love to be down at the 1-kilometer resolution, basically down to, you know, standard city big blocks, right? So the distance between Speedway and Grand, or Speedway and Broadway, right? But we're not quite there yet, but wouldn't that be fun? So we know it helps when we add the resolution. So here's 200 kilometers. You basically don't even have a coast range, just sort of a blob where the Rockies are. Here we've got a coast range, and we've got some of the Rockies as well at 50 kilometers. And of course, this is what it would look observationally. This is the difference in precipitation in Europe. Here it is with the blob of 200 kilometers. Here it is when you actually use a 50-kilometer atmosphere. And we're actually running at GFDL now a 25-kilometer atmosphere. Although I've got to say it needs some work on some of the parameterizations, because as we get down in relative size, certain of the physics that was captured by, say, a fudge, we now are resolving, so we don't need to fudge it. But if you keep using the old fudge, it's already got some of the new stuff in it, so we have to redo that whole parameterization from scratch, which is wonderful and awful all at the same time. Very hard work, I might add. I just got back from my sabbatical, and that was exhausting. So this is the thing I was working on, which is the Southern Ocean. So what we notice is the eddy kinetic energy observed, there isn't any in the old 1-degree models. We had a parameterization that had something like eddy kinetic energy in it, but we now have it for real in the new ultra-high res models. And this is that 10-kilometer ocean I was telling you about. So basically, we've come through Manabe-Bryan with the first climate model in 1970 to the climate model in 1984, CM 2.0 and 2.1, which is what I worked on when I was at Princeton. And then they went through a whole iteration when I was not there, but just working from afar. And then on my sabbatical, I've been working on these guys. So just so you know where we are error space. So here is the model that we developed last time, the 2.1. And this is increasing error. And these are models from this is China, this is NASA, this is the National Center for Atmospheric Research here in the US. This is the Germans, the French, the Russians, the Canadians, etc. Basically, everybody there is. And here's the observational error. That's where we are. We're getting there. We're not quite there. We're making improvements, but we're in range with the better models. Now, you could argue that we're not so much in range if you were using one of these poorer models, but we're really down here. So the data center here at UA, I just want to make a little plug. We actually have a brand new data center here on campus that's able to handle some of our big runs, which is fantastic. And our students are able to run them, which I find amazing. I have a fantastic grad student here that's on a NASA fellowship, and he's actually taken this code and adapted it, get this, for Titan's atmosphere. So cool. Right, and we have lakes of methane that circulate. Woo! Hence why I hang out over here. So cool. And he went to GFDL, where I used to work, and actually did a summer workshop, and it helped launch his whole atmospheric model. It's been really fun. So, and I just wanted to show you a couple of the GFDL data portal. It's all available if you would like to see anything we do, basically. Other than the most recent development, everything eventually makes it online pretty quickly, actually. So the reason I worry about that Southern Ocean, remember those errors? Some of them were really big and some of them were really small. This is what they look like in the Southern Ocean. This is what I spend my life working on these days. Is I don't want to go back to sea down there. Oh, please don't make me. But the problem is the models aren't quite there yet either. The better ones are, but we are trying to get the rest of our community to pull up their boots. It's, or bootstraps, whatever you want to call it. We're behind. Transport through the Drake Passage. Remember I told you it was 172 Sverdrups, 172 million cubic meters of water a second? They've got ranges from 30 to 336. Oh, it's terrible. I don't mean to beat up on my colleagues, but Okay, so, and we have another problem. Here is our total max winds. So this is what they should be, and this is where we are in our two models that I've been using from GFDL. And here is what the transport in the Drake Passage is, and it should be roughly in here. And of course, this is what it looks like. It's scattered all over the map. We've got a problem, don't we? So we have some new tools to look at. Oh, and just by the way, if you think the winds don't matter, here's the difference between a weak wind case and a strong wind case. A weak wind case where the winds are basically too far equatorward, and we're trying to poleward shift them over time. And when we do, it's like turning the US off. The total amount of heat storage in the ocean decreases. This is the difference in the heat storage. How's that for a kick in the pants? I mean, sorry, but it's true. You really have to get the Southern Ocean right to know how much heat this ocean is taking up. And what it does is it changes the climate. Here is our weak wind case, and here is our weak wind case, and here's our strong wind case. And notice how much more blue there is in our strong wind case. So the better your winds, the better the ocean mixing, the better the Southern Ocean looks. And the cumulative heat uptake difference is enormous between a case where you don't have as good winds and ones where you have this poleward shift. So the poleward shift is absolutely vital to getting the actual change in heat storage and the actual change in heat and carbon storage as well. So the potential impact on climate, both big and very substantial and really related to how well we do the wind-ocean interaction. So what new tools are we using to address this? We have a new, being put into place, Southern Ocean Observing System. And this includes 60,000 of these remote floats that basically do profiles. They sit down at 1,000 meters, and every once in a while they come up to the surface, they go all the way down, they come all the way up to the surface, and then they beam the data back by satellite. The problem is they can't go all the way to the bottom. The earliest versions only went to 700 meters, hence the problem with everything deeper than 700 meters. But it meant that we didn't have to go to sea, so yay. So finally we got it to 2,000 meters, and the current Argo floats go to 2,000 meters, which is great. But the Southern Ocean, remember where I showed you all the heat was going? Where was it? It was 3,000 meters. And the problem is the sensors go wonky once you put them under that kind of pressure, right? Once you start compressing them that hard, I mean, think about it, 3 kilometers deep. Basically, we need to talk to James Cameron, who just built the submersible. But seriously, we're working on this right now. One of my close colleagues, Kevin Spear at Florida State, is actually working on a new deep dive float that might be able to do this. We've also got new moored arrays. We've got ship of opportunity lines where cruise ships, shipping ships, anybody we can get to actually carry floats and drop them off the back end. We've been borrowing, and stealing and making our poor grad students, stay up all night for weeks and weeks, come home, whatever. They can do it. In fact, most of the time they ask us if they could, please, can I go to sea? I'm like, you won't like it. They're like, I will, I promise. So we also have new drilling going on in Antarctica to look at past climate and repeat hydrographic sessions like the ones I went on, and combined crossover points where we have both moorings and lines, which is always very valuable. We also have, just like they have in the atmosphere, a reanalysis where they take a model, a light model, not a heavily ham-handed model, but a light model, and they basically assimilate all the data into it to get the best estimate from data and model together. Now, the models I've been showing you have no data in them, basically just the forcing and then just the math, right? In this case, we're taking all the observations too to get a best fit. And they've done a beautiful job with the Southern Ocean State Estimate. It's like the first of its kind of this high resolution for the Southern Ocean. And it helps us understand where we don't have enough data, right? Where there's a lot of uncertainty and where there's very little uncertainty. So this is really exciting. And this is one of my colleagues who's also working on this new project. And then, of course, we've got our ultra high resolution models. And I just wanted to show you a little snapshot. This is a dye experiment where we basically dumped a bunch of dye into the model in the Drake Passage between Antarctica and South America, and we're just watching to see it go around Antarctica. It turns out the timing for floats is, it takes 8 years to get around. And the timing, and this was one of our first efforts, the timing for this was 8.1. So we were delighted, over the moon, that basically the current speeds, et cetera, and the general paths on an average with a bunch of virtual floats did pretty well. So we're also doing a massive Southern Ocean Model Intercomparison project with the Working Group on Ocean Model Development, sponsored by the World Climate Research Program. I know that's a mouthful, but basically we want to know how well the models simulate the Southern Ocean. This is something I work on a lot. What changes occurred in the Southern Ocean in the historical period, and what changes in the Southern Ocean are projected for the future. And these seem like basic questions that I might be able to tell you the answer to. But even if I could, wouldn't you feel more confident if I could get all my colleagues in Russia and China and everyone to simulate it themselves in some reasonable fashion that made us all feel secure that we had replicability, we were reproducible. It didn't matter what model for whatever. So that scatter worries me. I have what I think is the answer based on data and very, very careful modeling, but I would like to get my colleagues to try this as well. So we're working on this global intercomparison project, which is funded by the World Climate Research Program and partly by the NSF. And the co-chair of our working group on climate modeling, the CLIVAR, is actually helping me and Ron Stauffer from GFDL do this. We also have a joint US CLIVAR, which is an ocean carbon biogeochemistry working group, which are two of the main interagency working groups. And we've got this big fit. You don't recognize them, but these are the best of the best on the Southern Ocean, and they've all agreed to help work on this problem together because we think we've got a real problem. So we've actually come up with the metrics that each one of them in their particular area thought was the most important thing, and there's a paper coming out in the Journal of Climate on this. Basically the metrics. How would we know if we got it right? What would you absolutely have to simulate to know that you had a great Southern Ocean? So we have some great input and some fantastic results. And then we're doing this other project, which is the Center on Southern Ocean Biogeochemistry Observations and Modeling. And it's through the Science and Technology Center program at the National Science Foundation, but they, in their infinite wisdom, had to dump us out of that program and back into our division program because of the sequester. So the project is funded, but not through the center thing. It's going to be funded as a virtual center through polar programs, which is fantastic. I can't complain. It was only a small budget cut from 25 million to 21 million. That's okay. But all the modeling here, this group, is centered at the University of Arizona. So we are the lead for that. Princeton is the lead for the center as a whole, and we're the lead for the modeling, and Scripps is the lead for the observations, which is pretty exciting. So this will be our new big project, and I thank you for listening.
Thank you, Joellen. And let's see, we have a microphone around. If there are questions.
Oh, I didn't know you that well. Come on.
Can you discuss the implications of the uptake of carbon into the ocean, as well as the warming of the oceans?
So, at the moment, the wind change is trumping the change in, it is warming, but the mechanical forcing of the winds, because they've intensified, has actually beat the warming at this point. But most of the simulations, and I could have showed you some of these results, show that eventually, with high enough CO2 in the atmosphere, it will end. It will cap. It will basically cover up the deep mixing, and it will happen no more. And it depends on how fast we put the CO2 in, basically the total cumulative amount that's put into the atmosphere that warms the ocean. Seems to be the only major limiter, because at some point it just overwhelms the system, because you get a thick enough layer of warm water in the summer, basically cannot be penetrated even with the mighty Southern Ocean winds. And that's projected to happen, depending on the model, between somewhere between 2025 or as late as never, 2100, as far as we run the simulations out. So that the uncertainty there, the models I work with say that it really depends on how much CO2. If we just double the CO2, and remember we're already over 400 parts per million, right? We hit that last year, just this year actually. So it's really a matter of how much. Eventually, we're in kind of a tiny moment of grace where the warming is not quite so quick because the winds are driving the ocean to take up more. Eventually, that will end, and we'll be on a more aggressive warming path. There's a depressing answer, sorry.
You told us there are large uncertainties. You also told us that there is a model or a number of models which predicts things, and the full understanding is still not there. Nevertheless, I would like to ask you that based on your knowledge and your experience, what do you expect to see 10 years from now and 20 years from now in terms of the effect on the atmosphere?
Well, I like to average over 10 and 20-year time scales. So if I took the next decade, I'd do basically like the Weather Service has done with the data they have so far. When they dump the last 10 years, we take 30-year averages, and in 2010, we basically stopped looking at the 70s and started looking at just the 80s, 90s, and 2000s for our 30-year average. And when they did that, it was drier here and warmer here. Because the long-term average, when you lost the 70s, all of a sudden looked drier and warmer. My guess is that when we drop the 80s, it will look drier and warmer. When we move forward another 10 years, it will look drier and warmer. That is my expectation, and it is consistent with every analysis that I have seen done with a reputable model or estimate. CO2 controls, because CO2 in the atmosphere basically makes the greenhouse effect stronger. There is almost no way to see this change. While the ocean does take up a fraction of the CO2 growth, it's taking up a fraction of the growth. It's not reducing the amount of CO2 in the atmosphere. And as long as the CO2 in the atmosphere continues to accumulate, we will see warming. And unfortunately for us, warmer atmospheres, right, they don't like to rain. They will rain in rainy places, and they will be even drier in drier places. So my expectation is that as we warm the tropics, we'll ramp up the Hadley circulation, which will rain a lot in the tropics and make it even drier here. That's just consistent with everything we've seen.
Other questions? See if we can get her to say something else optimistic.
Hey, I live here. I think we're great at adapting. I think we'll be all right. But
I have a question about your probes. How long do they last? What do they run on? Do they get eaten by whales? Do they interfere with marine life?
they actually we worry about marine life interfering with our probes because, of course, fouling is the #1 death knell of most ocean-going materials, because you put them up in the surface layer, and of course things grow on them instantly. It's just a big soup of lovely growing things. So what we do is we have them float with the current at 1,000 meters. And it's dark down there. There is no photosynthesis, and nothing grows on the float, perfectly foul-free. And there are no whales down that deep, or very, very, very few of any variety. So at 1,000 meters, 10 football fields down, you're basically not fouling, not interfering with marine life. And what it does is it goes down and comes back all the way to the surface, and it beams its data back in 8 minutes now with the Iridium satellite improvements. And it's run on basically lithium batteries, just like your computer or laptop. And they last 5 years. In fact, our batteries actually are lasting longer than we expected, 7 years, and we've been able to add 4 new sensors to the float and still get 5 to 7 years on our floats. One of the great things about that is just, so with those lengths, you have to find a clever way to get around the fouling problem. And we feel like we've totally found it. That's such a great question, because that has exactly been the death knell of a lot of long-term sort of missions, like moorings, because stuff near the surface just grows all over it, and then your sensors don't work anymore. They drift horribly. And this has cut down on the drift to the point where we can use them for climate change type research. So look at the nitrate, the pH, the acidification, and the carbon content of the water without worrying that we're getting some gunky, algal crapola on our lovely sensors. It's so cool.
Hi, I had a question. What you said was pretty dire. Are we going to look like Vegas with 2 or 3 inches of precipitation a year in the next 20 years?
Arizona might look a little drier, but of course Tucson has this wonderful double, we get rain 2 seasons. So while our winter rain, which does keep our trees alive and is very important, we might see a decrease because of this westerly shift. We do hope, and it's still pretty uncertain because monsoon dynamics are not all that well understood. There's a lot that's understood about them, but projections are hard because they're very regional and very localized. But the expectation is that the monsoon, the tropical rain in the summer, will increase. So in fact, in many ways, we turn our little oasis green, right? Because we drip line our plants, we water our trees, we water our golf courses. So we've turned our little bowl, of Tucson, sort of the big basin here, is lovely. I wouldn't particularly want to live on the griddle up in Phoenix. But Tucson, I expect to be a lovely oasis in the desert for as long as I'll be around, so.
One more question. Is the Gulf Stream going to be affected by all of these changes too?
So it has been. It turns out that the Gulf Stream actually has been shifting, the extension has shifted slightly further north with this poleward shift in the winds. And the kind of water, the deep water that's formed up there is forming in a slightly different basin. Normally it forms in the Greenland, Iceland, Norwegian Sea every winter, and lately it's been kind of alternating between that and the Labrador Sea. Now it's still forming, still fantastic, still going gangbusters, but because the winds have moved a little bit, the location of the deep convection has moved a little bit. But it's actually very, very much connected to the same processes we're seeing in the Southern Ocean, except there is no up in the North Atlantic, there's just a down. So that is a little more sensitive to warming, of course, than this mechanical wind pumping. But nonetheless, we don't expect the North Atlantic deep water to flatline or anything anytime soon. That's one of the new results out of the last 2 reports was, hey, the consensus is with both our models and our observations that North Atlantic deep water is healthily being produced and continuing. There is no day after tomorrow.
Probably one more question right here. Can you wait for the microphone?
Are there any projections on
Wait for the microphone.
Has anybody made any projection on the growth of or decline of fisheries based on this information?
Yes, we are. There have been a few. I wouldn't say a lot, mostly because we had to get from phytoplankton. Notice I said phytoplankton and krill, and I didn't say fish and whales, because as we go up trophic levels and add complexity, it does become more difficult. However, it has been done in experimental mode at several of the major national labs. And what we see is not well, 2 things. One, we do have a problem with overfishing, and that can't be done in a model because it's a choice of humans. We can regulate it, not regulate it, do it, not do it, et cetera. But when we look at just the natural fisheries without our additional pressure on it, while some species are going to see significant decline because of global warming, and there are also ones that will win, that prefer warmer waters. So right now, the current projections, short-term projections, are winners and losers. There are some winners, there are some losers in fisheries. At the moment, though, what is trumping all of that is the overfishing. Everywhere in the world outside of the Ross Sea near Antarctica is having significant problems with overfishing. I mean, basically everywhere. There are very few what they would call well-managed fisheries, and I get this from both my NOAA colleagues as well as the actual fishing management journals, which tell me that we're really looking at some pretty significant declines in larger fish because we've gotten so good at catching the big ones.
Okay, let's thank Joellen one more time. And I want to thank all of you for coming, and we will see you again next year.